Hello everyone. We're going to go over how to solve a circuit using AC analysis. Now, to do these kinds of problems, you should be very solid in how to do DC circuit analysis using superposition, using the node voltage method, using mesh current method, and knowing how to do Thevenin-Norton transformations. So for DC circuits, you should be solid on that, and then it's a very easy translation to go into AC circuits. So in this example, we're supposed to find the node voltages VA of t and VB of t. Okay, and VA is here and VB is here, in between the inductor and the current source. So now this circuit is stimulated by two independent sources. One of them is a voltage source, and its value is 10 cos 50t, and we have a current source whose value is 5 sine 50t. Okay, and we have a capacitor, an inductor, and a resistor. So we will need to use AC circuit analysis to solve this. So to get started, let's put the circuit for reference on the left hand side. Okay, so that's the circuit. And now let's label the circuit elements symbolically, because what I'm going to do is solve this symbolically so you see how AC and DC analysis are related. Okay, so let's start labeling these circuit elements symbolically. Okay, so now the voltage source, V of t, is equal to 10 cos 50t. I'm going to label it symbolically as the voltage phasor, V. Okay, the current source, I of t, equal to sine 50t. I'm going to label that as the current phasor, I. Okay, so then what about the capacitor? So we have a value of 1000 microfarads, but I'm just going to use a general symbol, Z, for impedance, and I'm going to call it ZC for capacitor. And then for the inductor, I'm going to call it ZL. Okay, now for the resistor, I can call it ZR if I like, or I can call it R. Okay, I think I'll just stick with R, but I could have called it ZR. That would be perfectly fine. Okay, so now let's put that symbolic circuit on the left-hand side as well. And what we're going to do is we're going to write the node voltage equations symbolically. And we're going to see that it follows the exact same format or same pattern as we saw for AC analysis. Okay, so let's do node A. Okay, so now for node A is right here, and this is the voltage, VA. Okay, so now when we're doing node voltage, right, we write the node voltage equation in terms of the currents flowing out from the node that we're on. So let's look at this current flowing to the left. Okay, so that's denoted by my equation here, flowing to the left. Okay, so now with node voltage analysis, we always start with the voltage that we're on at the node as a term on the left-hand side in our numerator, VA. Okay, and on the other side, we see the voltage V, so it's minus V. So it's following the same pattern. And then the circuit element, normally it would be a resistor, but in our case now we have ZC, and that's what appears on the bottom, ZC. Okay, so that is exactly the same pattern that we see in DC circuits. So now let us do the current going down. Okay, so that's VA on top, and then the ground reference on the bottom, so it's just VA. Okay, and then the circuit element is this resistor R, so that's what appears here. Okay, so that's quite straightforward. and you can see the current flowing this way. That's this one. So we just have VA minus VB divided by ZL. Now, that entire equation has to equal 0, okay, because of KCL, so it's equal to 0, okay? So let's go to the next step. We're going to do node B. So node B follows the same pattern, and we see there's only two currents, okay? We have one current going to the left, that's this one. So it's just VB minus VA divided by ZL. So that's exactly the same pattern that we would have seen in DC circuit analysis. And then we have the current flowing down into the current source. And that current source is denoted as I, the phasor I. And because the current is flowing in the opposite direction of the arrow, we say that we have a negative sign in front of the I. Okay? So that is the equation for node B. So we have two equations, equation 1 and equation 2. So we can see that the basic circuit analysis is the same as for DC circuit analysis. So now, there was something odd, wasn't there? Right? What is negative I, this negative I phasor? Now, is it different than just a positive I phasor? Okay, and we said that the current is flowing up, right? But this is a sine, and when sine is positive, the current would be flowing in that direction, but when sine is negative, the current would be flowing actually in that direction, wouldn't it? So we're going to come to this later, okay? But why don't you think about it to see what's the meaning of a positive or negative current phasor or voltage phasor. Okay, so now let's move on with our analysis, and we're going to develop the expressions for the phasors and for the impedances. So for the current phasor and the voltage phasor, and for the impedances at C, ZL, and R. Okay, so then let's do the voltage phasor. So the voltage phasor, is here. The voltage phasor is here. Okay, and this is the expression. So this is the time domain expression that we got from up here, okay, for V of t. And then we can note that we can write that with a phase angle of 0, okay? So it's added a phase angle of 0. And when we write the voltage phasor, this is what we do. We take whatever the coefficient, whatever is in front of the cosine, and we drop it down, and that becomes the magnitude of the phasor. Okay? And then what we do is we take the phase angle in the argument for the cosine, and then we bring it and we make that the angle. And then that's it. Okay? So what happens to this 50? So that 50, as you might recall, is omega. And that disappears when we translate to our phasor. Okay? Now, it's still part of the system. That 50 doesn't go away, and we'll see that it comes back later when we make the final expressions for VA and VB. Okay? But when we're translating it to a phasor, that omega drops out from the expression. It's implied. Okay, so then let us label V with the value that we found, and then move on to the next element. So now we're going to do the current phasor, I. Okay, and we start off with the time domain expression here. I is equal to 5 sine 50t. Okay, so now there's a problem because it's it's a sine, okay? And what we have to do is convert that sine into a cosine in order to be able to write the phasor form, okay? All of the phasor forms require that the function be written as a cosine function, okay? So we can't use sine directly. We got to translate sine into cosine. And how we do that, how we convert sine to cosine, is by adding a minus 90 to the phase angle, okay? So what's happening here? Let's just write that really quickly. So imagine we have our graph of sine. So sine is going to go something like this, right? And we have a cosine, right? Cosine goes like this. Okay, and then what we're going to do is we're going to grab that cosine and move it 90 degrees to become sine. Okay, so when we take this cosine, so let me just label it. So this is cosine, and this is sine. So when we move the cosine 90 degrees to the right, that's the same thing as subtracting 90 degrees in the argument, okay? So you should be very clear on that, okay? And if you're not, you should just work this out so that you're comfortable with it. So then, now that we have that, we do the exact same procedure as we saw last time. So whatever is multiplying the cosine drops down, and it becomes the magnitude of the phasor representation, and then the phase shift drops down and becomes the phase angle, okay? And the 50t, or the 50, the omega, drops out from the phasor representation. Okay, and now that we've found that, let's label that in our diagram, okay? So that we have a record of what we calculated. Okay, so we've got the two sources. So now let's work on the passive elements, which are the capacitor, the inductor, and the resistor, okay? Those are the passive components. Okay, so R we know is 10 ohms, so we can just write that directly, so that's very easy, and that's a real number, okay? And we can just plunk that in right there. It's 10, okay? It's a real number. Now, all of these things that we're gonna put into these equations up here, right? We're gonna put in the values. Okay, so that's what we're working towards. So now let's do the write the expression for the capacitor. Okay, so now the capacitor, its value is 1,000 microfarads. Okay, and the equation for the impedance of the capacitor is 1 over j omega c. Okay, so we know the capacitance, okay, is 1,000 microfarads. We know omega as well, don't we? Okay, so let's start with the capacitor, okay, that's 1,000 microfarads. And then we know omega, which is 50 radians per second, and it comes from the expression 10 cos 50t, and also from 5 sine 50t. So now the thing is, note that both have the same frequency, 50. 50 radians per second is the frequency. So now, whenever you see problems in our course, you'll always have the same frequency, okay? So you're not going to have, like, you know, cos 20t and sine, you know, 50t or anything like that. It's always going to be the same. and it's going to greatly simplify our phasor analysis, okay? And it's very difficult to do phasor analysis if you have different frequencies, okay? So let's just keep going and plug in those values into our equation. So we're going to use this equation, right? ZC is equal to j omega c. So now we've got it down here. So we have on the bottom j times 50, which is the frequency, the radian frequency, and then times 1,000 microfarads, okay? So you should also know your multipliers for micro, milli, and whatever, okay? And now when we compute that, that comes out to minus J20 ohms, okay? So that's the impedance of the capacitor. So then let's put in that value here so that we label our drawing with all of the values that we're calculating. Okay, I hope that's straightforward so far. So now let's do the impedance of the inductor. Okay, now the inductor equation is ZL is equal to J omega L, okay? And we know that omega is 50 radians per second, okay? We found that earlier, we talked about that earlier, so that's the 50 coming from the sources, okay? And then we know that L is 400 millihenries, okay? So we know it's 400 millihenries. And then we can just plug into our equation. So it's J times omega times 400 milli, okay? And that works out to J20 ohms. And then we can put that into our equation, or label into our diagram so that we have it. Okay, so now we've calculated all of the phasors and the impedances. So now what we're going to do is just start plugging into our equations. So now we're going to work with equation 1, and we're going to put in the values that we found. So we're solving for VA and VB, okay? And we're going to solve for the phasors VA and VB, okay? We're solving for that, but we know all the other values, okay? We found the voltage phasor, we found ZC, we found R, we found ZL. So we're just going to plug those values in into this equation here. So we know that the voltage phasor is 10. We know that ZC is minus J20, R is 10, and ZL is J20, okay? And then now we're just going to manipulate this equation, okay, just like we would do in DC analysis. So now, next step, to simplify it, let's get rid of the denominator, okay? So if we multiply by J20, we get the expression that you see here. Now the minus sign here goes upstairs, and then the denominator gets canceled, okay? So that's gone. So then we're stuck with the VA phasor minus 10, okay? And then we can see that just multiplying J20 results in the equation that we have here, okay? So then we can simplify it. Okay, we can simplify this, work it out, and we get J2VA minus VB being equal to minus 10, and we can call that equation 3, okay? So that's an intermediate equation that we're going to put up here so we don't lose track of it, okay? And now we're going to use equation 2 and put in the values for equation 2, okay? So our VB and VA are unknown. That's what we're solving for. But we know that ZL is J20, and we had found the current phasor to be 5 with a phase angle of 90 degrees, okay? And then we saw that the negative sign is here, okay? So we didn't lose that out. So all we're doing is plugging in the things that we found. But we have a problem. We have a problem here. So how are we going to manipulate the equation that we've just developed, okay? The problem is that this is in mixed rectangular and polar form. So this one here, this is in rectangular form, okay? And this is in polar form, okay? So we need to convert it one way or the other. Okay, now we can't really add or subtract in polar form, so we convert the polar form into rectangular form in order to be able to add or subtract, okay? Multiplication is great in polar form and division is great in polar form, but if we're adding or subtracting, we want to be in rectangular form. So let's convert into rectangular form. And what we're converting is this 5 with a phase angle of minus 90. And then, so what we can see on the complex plane, we have a magnitude of 5 and a phase angle of minus 90. So that results in a vector going down on the imaginary axis, going down, so that's what the minus 90 represents, okay? So I guess we can put a minus 90 there, okay? And then its magnitude is 5, okay? So now be clear that I've ignored this negative sign, okay? What I've got in this phase diagram is only this part, okay? So now let's continue, and we've got now the real component is 0, right? Because it's 0 on the real axis, and on the imaginary axis it's minus J5, okay? So that's what that point represents right here, okay? That's what that point represents. 0 minus J5, okay? And that is I. Okay, so then we're going to plug that result into that equation. So we're working with that equation, and we've put in this minus J5 into there, okay? We don't have to write the 0, it's just 0. And note that this negative sign has dropped down, okay? So then we just operate, and we multiply by J20 to get rid of the denominator, and we get the expression VB minus VA minus 100, and then just rearrange to get equation 4. So VB minus VA is equal to 100. We just brought the 100 to the other side. Okay. So then we have our two equations. These are intermediate equations that we've developed, equation 3 and equation 4. And what we're going to do is we're going to add them up, okay? And then you can see that when we add it up, we're going to get rid of VB. Okay, so VB is gone, and now we're stuck with an expression with VA. So now we can go ahead and solve this, okay? So we can just do some manipulations to solve for VA. So if I factor out VA, we get this expression, VA times minus 1 plus J2 being equal to 90. And then we'll just bring minus 1 plus J2 into the denominator, okay? So we put it into the denominator. Okay, so that's pretty straightforward. And then we have a problem here, because to get an expression for VA, we're going to have to convert VA into a standard form, okay, to work with it. So we can't have any imaginary numbers on the bottom, okay? So we want to have it some real number plus an imaginary number. So how do we do that? How do we fix it? Okay, so this is something that you should know for basic manipulations, and that is you got to multiply by the complex conjugate of the denominator. Okay, so this is the denominator, and we're multiplying by the complex conjugate. Well, in fact, the complex conjugate divided by the complex conjugate. So now, this part here, okay, this is equal to 1, okay? It's just the same thing divided by the same thing, okay? So we're not changing this number, okay? Because we can't change it or else it'll be a different number. So we have to, so we're multiplying by 1, but why do we multiply by the complex conjugate? Okay, when we multiply by the complex conjugate, so the denominator is going to work out to be a real number, okay? The j's will disappear, okay? So that's why we have to multiply by the complex conjugate, and how we form the complex conjugate is that we flip the sign on the imaginary part. So this was a plus, okay? This is a plus, so then it becomes a minus. If it was a minus, then it would become a plus, okay? So that's just a little refresher on the complex conjugates. So then we multiply it out, and one thing you notice, okay, we end up here with 1 plus 4, and that's a real number, okay? If you do this operation, and if you end up with an imaginary number in the denominator, then you know you've done something wrong. And so anyway, we can continue working this. So 1 plus 4 is 5. So then we can easily divide the real part and the imaginary part by 5 to get it into standard form, to get VA into standard form, and it works out to VA being equal to minus 18 minus J36. Okay, so we're getting close. We've got some value for VA, which we'll have to convert eventually to a time domain, right? Because what we have to do up here is get a time domain expression for VA. So right now that's an intermediate expression, but we're going to use it to solve for VB, okay? So now, if we take equation 4 and plug in the value that we developed for VA, okay, so we're going to plug that in right here, and then solve, okay? So this is the equation, okay? So we're going to solve for this, and VA becomes equal to 82 minus J36. Okay, so that's great, but to find the time domain expressions, you know, VA of t and VB of t, we have to convert this rectangular representation, so these are in rectangular form, we need to convert it into polar representation. So this is really important. We have to convert it to polar, and then from polar we can convert it to the time domain. Then we can get this final form, okay? And we're going to see how that's done. So you should be quite familiar with this process when you're doing these kinds of questions. So then, let's represent these two phasors in the complex plane, okay? And so then so that we can easily find the polar form, okay? So when we do the polar form, we want to find the magnitude and the angle, right, of each one. So this, of course, is for VA, and this is for IM, okay? Or sorry, not for IM, for VB. Okay, IM is of course the imaginary axis, and the horizontal is the real axis. Okay, so then how do we convert to polar form? Okay, to find the magnitude, we can just use Pythagoras. Okay, the square root of the x and y components, or the real and imaginary components. Of course, it was minus 18 and minus 36, but I dropped the minus signs because we're squaring them. Okay, so that's how you calculate the magnitude. So the magnitude is very easy, and then we have to calculate the phase. So then the phase, how I've calculated it here, is I'm going around all the way here, and that is my minus 180 degrees, and then I'm coming back here, and that is the inverse tan or arctan of 36 divided by 18. So you'll just work out your trigonometry however you do it. There's different ways of doing this, so this is one way of doing solving for theta. Okay, so this is how we convert rectangular to polar form. And then I've repeated the process for VB, where we have the magnitude is 36 squared plus 82 squared, and then all square root. Okay, so that's the magnitude M, right? That's the magnitude M. And then the tan is pretty straightforward. I mean, rather, the phase angle is very straightforward. It's the arctan of minus 36 divided by 82. Okay? And that gives us theta, the phase. Okay. So then, what we do is do the computation. So VA becomes equal to a magnitude of 40.25 with a phase angle of minus 116.6 degrees, and then VB becomes 89.55 as a magnitude with a phase angle of minus 23.7 degrees. Okay? Now, the next step is super easy. So this is really great. Once we get it in polar form, we can easily write the time domain expression. So all we do is we bring down the magnitude in phasor form, and that becomes a multiplier in front of the cosine. And it's always cosine. It's always cosine, okay? When we convert from phasor to rectangular form. And then the phase angle in the phasor form comes down and becomes the phase angle in the argument. Okay? So then, the other interesting part is what happens, how do we get this part, the 50t, okay? Where does that come from? That's omega, okay? And that comes from way over here, from the original expressions that we had. So that comes down. So let's maybe use a different color. That comes down all the way down here. Okay? So that's that 50, that's where omega reappears again into this calculation. Okay, we do the exact same thing for VB. So the magnitude of the phasor comes down and becomes the multiplier of the cosine. The phase angle comes down and becomes a phase angle in the argument. So minus 23.7 degrees, minus 23.7 degrees. And then 50 is omega. Okay? So now, that was that. Okay? So that is the final answer. We have the time domain voltages for VA and VB. Okay? So then, let's do a couple little things. Let's consider. Now, just to get a little bit more practice, I'd like to show you a couple ways to solve for VAB. Okay? So what we did just now is solve for VAB using the complex conjugate, right? We use a complex conjugate. We got an intermediate form. We worked it and found the rectangular coordinates, okay? Then plotted that on the complex plane and did Pythagoras to get the magnitude and some trig to get the phase angle, right? And then what we did was drop down the magnitude and the phase into the time domain expression. Okay, great. So another way of doing it is shown on the right. Okay, so let's just imagine we take the phasor representation of the denominator. Okay, so this is what it looks like in the complex plane. Okay, -1 is a real number, so that's -1 over here, and then +2 on the imaginary axis gives you a vector like this. Okay, and then we can just calculate that complex representation in polar form for that vector, and it works out to be the square root of 5 at a phase angle of 116.6 degrees. So then, when we calculate 90 divided by -1 J2, we can replace the denominator with that polar representation, and then what happens is that this 90 divided by the square root of 5 becomes 40.25, okay? And then the phase angle, it's in the denominator, and when you bring it up to the numerator, it just flips its sign. So it becomes minus 116.6 degrees, okay? And just notice that there is like an implied phase angle here, 0 degrees and 0 degrees, okay? So if you had a phase angle up on top, you'd have 0 degrees minus 116.6 degrees. So you have to watch out on how you do your calculations, right? Okay, so then we obtained the time domain expression using the same method as before, dropping down the magnitude and the phase angle, and you will notice that they are both identical. Okay, so that is just showing you another way to calculate a value for a phasor. Okay, just to give you a little bit more practice or ideas on manipulations. So now, what did we talk about earlier? What is the difference between I and negative I phasors, or V and minus V phasors? Don't the AC waveforms go positive and negative? So what meaning does it have? Okay, so let's look at this a little bit mathematically. Okay, so our voltage phasor V was 10 with a phase angle of 0 degrees, and the time domain expression was 10 cos omega t. Okay, so then what does that look like as a waveform? That just looks like that. It's just an ordinary cosine wave with an amplitude of 10. Okay, so then what about a negative voltage phasor of the same? Okay, so minus V is just going to be minus 10 with a phase angle of 0 degrees, okay? And then, if we look at it in the time domain, minus V of t is just minus 10 cos omega t. So what does that look like as a waveform? So here it is in red. So we have minus 10 cos omega t, okay? So the difference between them is that one is a mirror image of the other, okay? It's flipped on the horizontal axis, okay? So that's what a negative sign in front of a current or voltage phasor represents. It's just a flip over the horizontal axis. Okay, so then what we can say also to interpret it is that a negative time domain voltage is the same as a positive cosine with a phase shift of plus 180 degrees. So what have we done there? We've taken this waveform and we've shifted it 180 degrees backwards, okay? And if I drew my waveforms better, they would line up perfectly. And what about minus 180 degrees? It's also equivalent to that. So that's as if I took that waveform and shifted it rightwards by 180 degrees. Okay? So that is the implication of that. Okay?